The chemistry of clear water. How do we even get clean water? Where do we get it from? We get water from lakes, streams and creeks, clear rivers. Wait, did I just say clear rivers? No, I meant rivers, seas, oceans, glaciers, more glaciers, but I guess they're way more north, reservoirs, groundwater, wells, and aquifers, and finally ponds. We can't just drink it straight from the source. For example, in California, they use a desalination plant. I'm not really sure how to explain it other than it looks like a combination of a train yard and a factory with tons of pipes. The first thing the plant does is remove unwanted particles from the water, then reverse osmosis separates impurities, including minerals such as dissolved salt, from the water. The final thing it does is add minerals and chemicals to the water to meet health regulations and standards. But that's just how that place does it. A different type is the DPR system. That's where human waste is purified into clean drinking water through multiple filtration and disinfection steps, effectively creating a sustainable water cycle. The final type of plant is called the FDPIR plant. This includes oxidation, biological activated carbon, and chlorination. The coolest is NASA's CL system. It includes vapor compression, dilatation, and catalyst oxidation. Okay, we get the point, but how does it get to your house? Source, transplant pipes, and water towers if necessary. The only issue is that it costs a lot of money to operate because of the energy it requires. In some places, rivers even dry up and some wetlands collapse. Some cool things that some transplants have is atmospheric water generators, graphene filters, and solar desalination. A atmospheric water generator is different from a normal one because instead of getting the water from the ground, they create water from thin air. This works perfectly in a desert. Graphene filters are different because their atoms are 1 atom thick instead of the normal 0.00001. Solar desalination uses solar energy to evaporate and then condense seawater, separating the salt and impurities from the water. Let's talk about the chemistry side of this. The first step is to remove suspended particles such as turbidity, organic matter, and bacteria, and they do this by putting aluminum sulfate, ferric chloride, and ferric sulfate into the water. Step 2 is disinfection. The common chemicals are chlorine. There's also a few others. It is hypochlorous acid, and that is the active disinfectant. That's basically what is going to clean up the water. We have chloramines. That is longer lasting residual disinfection, so I guess for a longer amount of time. And finally, ozone, which basically just helps all the other chemicals work together. For step 3, water's acidity is balanced using lime or soda ash to prevent metal pipe corrosion. Phosphates are added to coat pipes with a protective layer, stopping lead/copper from leaching into your water. This keeps the water safe and clean by the time it touches your tap. So basically the chemical is sodium phosphate and zinc phosphate, and the reaction is it forms a protective mineral layer inside pipes. And it works because it creates a barrier between water and metal pipes. Sometimes the pH level is way too high or way too low. So this step makes it in between 6.5 and 8.5 where it's safe to drink. Step 4 is fluoridation. Now, yes, not all treatment plants use this because it's basically a part of teeth. It's going to make your teeth better because they are putting fluoride compounds like sodium fluoride or fluorosilicic acid in tiny amounts, and this strengthens the tooth enamel by converting hydroperoxide in teeth to harder your fluorpyrite. And this reduces cavities by 25%. 73% of public water has this, while most of Europe rejects it, preferring toothpaste. And no, I'm not telling you to not use toothpaste. Please use toothpaste.